Hello everyone, and welcome to our project on quantum circuit transformations using reinforcement learning. So what does a quantum circuit look like? Well, it looks very much like a classical circuit with a bunch of qubits starting out, participating in one-qubit operations which are analogous to NOT gates, and multi-qubit operations which are analogous to AND gates or OR gates. The key difference, however, is that due to the no-cloning theorem of quantum mechanics, the states cannot be copied from the memory, operated upon, and brought back. Therefore, the CPU has to be built on top of the memory itself. So all qubit operations are not possible. 2-qubit operations can only be applied to qubits which are physically neighboring each other. In this example hardware topology here, 2 and 5, 2 and 4, 3 and 4, etc. can be operated upon, but 2 and 7 is an invalid operation since it's not local. Here we take the example of trying to compile down to this target hardware with 0 at the center. The initial circuit does not respect the constraints of this target hardware by having an operation on qubit 1 and qubit 2, which is not local on the target hardware. We can convert this circuit into an output circuit by adding in swap gates, which converts this into a valid operation but makes the circuit a little bit deeper. We are tasked with devising an algorithm which takes an input circuit and converts it into one which faithfully respects the constraints of the target hardware while adding the minimum possible depth in terms of the number of added swap operations possible. To represent our problem to the reinforcement learning agent, we take our input quantum circuit and convert it into a directed acyclic graph of dependencies. Each 2-qubit operation is a node in our graph, and 2 nodes are connected by an edge or a dependency if and only if they share at least one of their 2 qubits. Our model will start at the leaf nodes, schedule them on the target hardware, and pop them from the graph, and then keep on making its way iteratively through the rest of the graph. The evolution of state from the perspective of the agent is shown in this image. Here we show that the agent is scheduling several operations. The yellow and orange colors are used for C0 operations, whereas the green and the purple colors are used for the swap operations. And you can see that the agent evolves the state until it completes the set of tasks that it was assigned in 5 time steps. Since we want to minimize the total depth of the circuit and not just the number of operations, we need to build the idea of parallelization into our model. At the same time step, different pairs of qubits can parallelly enter different operations, but no 2 operations can share the same qubits. This is what makes our tasks different from games like chess. Chess has on average 35 moves at any time step. Go has 200, but our problem has over 2 to the power 16 operations we get to choose from. Other research attempts, scanty as they are, propose using a simulated annealer to search through the action space, which is guided by a deep Q network where a bunch of linear neural layers parameterize the system. We propose to replace this with a Monte Carlo tree search which is guided by a graph neural network. To solve the problem of searching in a combinatorial action space, we perform our Monte Carlo tree search in 2 stages. In the first stage, we take our default solution and one by one in an autoregressive manner set up different swaps into the solution. And finally, once we are done with this, we break out into the second stage, committing our operation, which was built up as a combination of individual moves, into the composite set of swaps and C0s that needs to be performed into the time step and update to the next state. Like all MCTS searches, we select a leaf node, we expand it out to the next state, we get our model to evaluate it, and then we finally back the values that we have learned from this update up into all of the parents of the node and train our neural network based on it. This method has obviously been inspired by the success of the same idea being used by DeepMind's AlphaZero amongst others. We use standard Bellman updates to update our value function and policy functions, together with a special form of upper confidence bound on trees, which is made specifically for asymmetric trees. We have a graph neural network to evaluate the value function, or how good a given state is. We take our state representation and put it through an edgeconf block, followed by a few concatenations and other dense layers. We use swish activations in our network since they perform better and computational costs are not a primary bottleneck in our model. Let's take a look at how we visualize the agent as it works through the graph, trying to improve it to at least human level accuracy. The green boxes represent the swap operations, whereas the blue boxes represent the 2-qubit operations. We constantly keep on seeing the reward function that is being shown on the right hand side of this first image, as well as the next targets, or in the 4x4 qubit case, the number of operations that have completed. And this is the primary visualizer that we use to validate correctness of our model. The primary value proposition for our method comes from the following facts. We present the idea of using mutex locks in RL agents to represent the state of parallelization to the environment and to the neural network. This helps us deal with slower gates like swap gates, which are 3 times as slow as other gates, by making the mutex locks integer valued. We also use a better representation method, providing more information about the state to a graph neural network, which exploits the fact that several of these parallelization decisions are local to a subpart of the graph. We hope to extend this in the future by using transformers for improving our long-term planning, but that's a little too expensive to train right now. Finally, the autoregressive setting provided by Monte Carlo Research leads to much stabler training and more guaranteeable results. We are very optimistic about the results of our method, since we have the best performance of all frameworks on IBM's large circuit realistic test dataset, and the third best performance on random circuits dataset. But this is expected, since our neural networks have a hard time strategizing for random gates, and the 2 methods which do better than us on this dataset are explicitly made for working well on perfectly random datasets. Finally, we are attempting to package all of this into publishable work very soon, and hopefully within the week we'll be able to offer this for download from our GitHub page and on pip by the name QRoute. We also hope to continue this research working on dynamic routing and consensus mechanisms in our neural networks, on future encodings using transformers, and on classical optimizations after the MCTS step is done, etc. If you are interested in this work or have comments, please feel free to get in touch with us on animesh.sena@research.iit.ac.in. Thanks a lot for your time. It was a pleasure presenting to you. Thank you.